Welcome to the Virtual Foundry podcast.
Hi, everybody. Welcome to the Virtual Foundry podcast. This is Volume 4, Episode 5. Today is Friday, April 21st, 2023. The time is 10:36 a.m. and the temperature is 50 degrees Fahrenheit here in southern Wisconsin. That's 10 degrees Celsius for you Celsius users. We are solidly in springtime temperatures, looking to be in the 50s, in that 10 to 12 degree range here for the next 10 days, and then we'll see what happens after that. But it's been a lovely spring so far here in southern Wisconsin, one of my favorite times of the year. Today on the podcast, we're going to be talking about the strength of green prints. Now, with me today, as always, is Brad Woods, founder, inventor, and all-around science guy. Say hello, Brad.
Hi, everyone.
And also with me today is Austin Triggs, our operations guy and right-hand man. Say hello, Austin.
Hi.
And I'm Tricia Cease, president of the Virtual Foundry. So we're talking about the strength of green prints. Now, what does green even mean? The filaments that the Virtual Foundry makes, and you can see a picture of those behind Austin there or to the sides of him. We start with regular 3D printing PLA and load it up with metal, glass, or ceramic powders. So they've got a really high material loading. So for example, copper is 90% copper by mass and just 10% plastic binder. So when you print with that copper filament, your print is 90% copper and 10% plastic. So that's what we mean by green. You've made your 3D print on your standard FDM FFF 3D printer, and now your print is that same combination of metal or glass or ceramic and plastic. So that's what we mean by a green print or a print in the green state. It just means you've just printed it, and that's all that's happened to it yet. Now, Brad, Austin, our Filamet, metal, glass, and ceramic 3D printed parts as strong as that same part printed in regular 3D printing PLA?
This is actually a tricky question. The shortest answer would be no. And it isn't as flexible as PLA, but in other ways, it has superior properties. It has better wear resistance. It has a greater mass. It has a slightly greater flexural strength, which is kind of interesting. One of the properties that we need this material to have in order to get it into a filament that can be handled without breaking is that it be reasonably flexible. So the primary reason we introduced this property is to make it so that the filament isn't brittle. It has a side effect of all of the green prints having a greater flexural strength than your typical PLA may have.
Now, we do have some video examples that involve a hammer to show you a little bit about what these parts can handle. So we'll take a look at those. The first one is a drop test. So we're just dropping a 3D printed copper part in what we call calibration rings. You can find this SDL on our website at the bottom of every page. So it certainly handles being dropped. Austin did this test earlier today, tried very hard to keep the dropped part in the frame, and it kept bouncing out, but it stayed in its original format. Next, we are hitting it with a hammer. So here's that same calibration ring part lying flat on a surface, and we'll come down with a hammer on that. So no problem there. It handles that hammer just fine from the top. Now we're going to look at this same part standing on end and see what happens with the hammer blow. Now, in that case, the part broke a little bit. So that leads us to the next part of our discussion, and that the parts will break. So Austin, tell us about if a green print is going to break, what will break first and how do we know that?
Yeah, so the first video of the hammer, you can see that it was hitting the part right on top, and it's a lot thicker. So it wasn't really going to do anything. I can bend this around all day in that direction, and it's never going to break for me. But as soon as I stood it up on end and hit the thinner pieces of the calibration rings with the hammer, you could see that it just broke right away because the part geometry changes how strong the part is, just based on like curves, corners can have a great effect on it, and then part thickness and density.
And it's true with any material. This is just part of material science. But a corner will focus the pressure. So like if you're pushing on it, it'll tend to break at the corners or where two walls intersect or something like this. And an interesting example is it's why there are no square windows on an airplane. They're always round. It's so that the stress isn't focused onto a single point.
Now, we around here like to carry parts around with us because it's just cool. These are the dice that I carry around in the bottom of my purse or in my pocket as I'm going through throughout daily life. And these are green prints. So they've had a little bit of finishing applied to them. For example, they might have been in a tumbler or hit with a wire wheel or brass brush or something like that. So they've had a little bit of finishing work done, but they hang out in the bottom of my purse on an everyday basis, and they are handling it just fine. You can also see that they're getting that standard copper patina, and what happens to metal over time naturally is also happening with these dice. We're seeing copper on the right and bronze on the left. Now, why is it important to know what the strength of green prints is? Well, in some cases, you might not need to go through that secondary step of debinding and sintering. And understanding green part strength helps make that determination. You can handle these parts a lot, as we're seeing. Now, one example of not needing to go through that debind and sinter process is with our rapid 3D shield tungsten filament. Now, that material was made specifically for the purpose of radiation shielding, and it provides that benefit in the green state. So no secondary heat process required. We have done a podcast about rapid 3D shield tungsten filament. I'll link that in the video here as well. Now, there's one word of caution. You cannot leave green prints in the sun or use them in hot applications. So Austin, walk us through what would happen in those cases.
Yeah, so with the binder is PLA compliant, and if you take a standard PLA print and let's say set it in your car on a hot summer day, it's gonna start to heat up quite quickly, and they'll deform. With our materials, they have a little bit more heat resistance than that, but they'll still do basically the same thing as PLA, especially in a hot car on a hot summer day, where temperatures are crazy high. And if it gets hot enough, you could actually just kind of smush it. One advantage to that is being able to kind of manipulate your print with like a heat gun or a soldering iron or a wood burning tool, where you can actually manipulate it and change its shape as you want to when you apply heat.
People often also ask us about the conductivity of green prints. Are they thermally conductive? Are they electrically conductive? Brad, walk us through those properties.
They are not electrically conductive at a low enough voltage to be useful. Let's see, what's the best way to describe it? If you look at our materials under a microscope, they look like millions of little metal particles with a thin coating of plastic on it. And this plastic puts enough distance between each of the metal particles that they are quite resistant to electricity. After sintering, they have the same generally the same properties as copper or whatever material you're working with, but in a green state, they do not conduct electricity in any useful form. As far as being thermally conductive, they're actually, pretty effective here, even in the green state. So our copper material, copper is one of the most thermally conductive materials there are. In our filament, the green prints have pretty decent thermal conductivity, but like Austin said, they don't tolerate high heat very well. So PLA, and this is true of all PLA, it has the glass phase transition point. I think it's maybe 150, 175 degrees. That's the point where the material becomes malleable and you can start to deform it. So it's quite low. But our material, as far as that property goes, is the same as regular PLA. So one interesting thing, I think, is that due to the thermal conductivity of the metals in our composites, you can actually print overhangs that you wouldn't be able to do with typical PLA. I mean, you can print nearly 90 degrees. It's pretty interesting. So thermally, definitely a pretty good conductor. Electrically, not at all.
How about magnetic properties of the filament and green prints made with high carbon iron?
Yes, this is cool. In fact, our iron material likely has the highest magnetic permeability of any material on the market. We tried to put some numbers around it. For example, we are seeing how much weight can we hang from this. And this is a chunk of high carbon iron and a neodymium magnet. And I'm not sure if I can illustrate how hard it's actually stuck, but it's very stuck. And here, when it snaps on, it's remarkable.
Yeah, we have a video that shows this attraction as well.
Yeah.
So that's another fun one around the shop here. We like printing with the high carbon iron and then messing around with magnets with it.
Right. And there's quite a few uses out there for this material in its green state. If you have a 3D print that you need to have some level of magnetic permeability, this is the stuff.
Now, if you don't need to debind and sinter your print, you can leave it in the green state, but you also want it to look great, you're covered. So there are lots of polishing, sanding techniques you can use to make your part shine. To get as far as you can go to a mirror shine on the metal. Now you're going to use the same polishing techniques that you would use with the regular metal that is in your print. So sanding and polishing, and we've done a podcast about this aspect of the 3D prints as well. So I'll link that video here as well. But here's an example of a fully polished green print. Now that square in front is a green print right off the printer. So nothing's happened with that one, and that's steel. And you can see Colossus there has had a lot of treatment with sandpaper, filing needles, and a rotary tool with some ZAM buffing compound. Am I missing anything, Brad, that got Colossus to this state?
No, I don't think so. And when you look at this part under a microscope, it's really interesting. So about 75% of the surface that you're looking at microscopically is pure metal. So it looks like metal because 75% of what's exposed is metal.
And it also has the weight and feel of full metal as well.
Yeah, the heft and the weight is an important property in quite a few applications. And we have people that use it for vibration dampening, counterweights, things like that, which you just wouldn't, which would be completely impractical with just plastic.
Now, the one trick to that polishing aspect and sanding and polishing a green print is it still has that plastic in there. So that same warning about heat that we talked about earlier applies here as well. As you're sanding and polishing, you want to make sure to move that friction spot around so that you don't actually start to soften and deform your print. Now, guys, what am I missing in the green part strength discussion? Are there any other points we need to cover?
Well, I think generally people often think that the green parts are going to be very weak and fragile, and they're not. They're not as strong as pure plastic, but they're much stronger than people may realize. This is this is our tungsten material. And what's cool about it is the fins on the inside. Each one is at a slightly different angle. And each of those fins is only 0.3 millimeters wide. And this part has been kicking around. It has some road rash, but it's been to trade shows with us. It's been in our parts box for 2 years. And it shows there's no breakage. It's starting to get a little sheen from being in my pocket, but it's strong enough to handle.
And Austin, you have a couple of green parts at your desk there that you wanted to show?
Yeah, I've got this is some chainmail that we printed I want to say at least 5 years ago, and we have not been gentle to it, to say the least. But each link is quite small and not held together by much, if you can really see that. And then the NASA chainmail, of course, this is 100% scale, and this has been kicking around for at least a year, and also we have not been gentle to it.
Wow, great. So yes, thank you. Those excellent illustrations of the green part strength. You can really mess around with these things quite a bit. So guys, I do have one more very important question before we wrap up today. Why are spiders so smart?
Got me.
Because they really know how to use the web.
Nice.
I like that one.
Thanks for joining me, you two, for this important discussion. And hey, out there listening, watching, if you have a cool project you want to show off in this format, we'd love to have you as a guest on our podcast, or if you would like us to do a deep dive on any questions that you have, we would love to do a podcast with or for you on that. Reach out to me at info@thevirtualfoundry.com and we can talk through that. Look for us on Reddit, Instagram, TikTok, Facebook, LinkedIn, Twitter, and we also have a Discord server. And in the Discord server, you can read about a lot of cool things that our partner innovators are up to. Go to the homepage of our website, thevirtualfoundry.com, and right in the upper left corner, you'll see a link that will take you right into that Discord, so you can check out what other people are up to. It's a very interesting place. Make sure to like and subscribe our YouTube channel, and until next time, happy printing, everybody.
Thank you.
Bye.